Hi guys, we're going to derive the Euler-Lagrange equation, which is the most fundamental equation in the calculus of variations. And before we do it though, let's take a look at an example that kind of demonstrates how this type of mathematics can be applied to the real world. Now the example that I'd like to use is what's called the Brachistochrone, and in it we're deriving the shape of a frictionless roller coaster that would minimize the time of travel from 2 points in space. Okay, so we see here that if we connect these 2 points with a straight line, obviously the distance traveled is minimized, but we don't have enough acceleration such that our average velocity is sufficient to minimize time. Unless, of course, one point is directly over the other. Okay, so we're not looking at that case. They're staggered. Okay, so now if we add a little bit of a curve, we have a much greater distance to travel, but we have a much greater acceleration such that our average velocity is sufficient to account for that additional distance traveled. Okay, so how do we go about deriving the shape that would minimize time? We're going to start by designating the optimal curve as y. We don't know what it is. That's what we're deriving. And an infinitesimal arc length we're going to designate as ds. So an infinitesimal arc along this curve is called ds. Now we know from algebra that the time of travel is simply the distance divided by velocity. But what happens when your velocity is constantly changing, which is the case in our example? So the velocity is here is different than the velocity here, which is different than the velocity here, which is different than the velocity here. So in this case, what we have to do is we have to take an infinitesimal arc length and divide it by the average velocity over that infinitesimal arc length. And that's going to give us an infinitesimal time. And then we take the next infinitesimal arc length and divide it by the average velocity over that interval. And that gives us another infinitesimal time. And we repeat until we've integrated. We repeat until we've done this over all infinitesimal arc lengths of this curve. And then we add them up. So we add up the infinitesimal times, and that gives us our total time of travel. Okay, so we have to rewrite this into an integral form. And to do that, we replace d with our infinitesimal arc length. And then we need to derive an equation for the velocity at each infinitesimal arc length. Okay, so to do that, we use the conservation of energy. So initially, the roller coaster has 0 change in potential energy. And as it falls, its change in potential energy gets converted into kinetic energy. And so mathematically, that's just saying that my change in potential is equal to my change in kinetic. So our masses cancel out, and we're simply left with an equation for a velocity of the square root of 2g times a minus y. Okay, so this is the equation that we're going to put in for our velocity. And so now we have to sum up all of these infinitesimal times. So ds over a velocity gives us a time. So now we have to sum them up through integration. And the bounds of our integration go from x is 0 to x is x naught. And we know from multivariable calculus that the arc length can simply be written as the square root of 1 plus y prime squared times dx. Okay, so what we have here is an equation that tells us the time of travel for any curve y. So no matter what the curve is that connects these 2 points, the time of travel under the influence of gravity is expressed by this. Okay, Now, what we want to do with the calculus of variations is we want to derive the function y that minimizes the time of travel, which is equivalent to minimizing this integral. Okay, so what we're going to do is we're going to derive the Euler-Lagrange equation, which is an equation that would be applied to what's inside this integral in order to minimize the time. Okay, so let me just write a couple things down here. Okay, so here we have j is equal to the integral of f, and f is a function of x, y, and y prime. Again, we don't know what y and y prime are. We're trying to find the conditions that y and y prime have to satisfy to minimize this integral. Okay, now here, let me explain this simply using our diagram here. There are infinitely many ways of connecting these 2 points in space. We can go infinitely many ways to connect these 2 points. So out of those infinitely many ways, how do we pull out the one curve that minimizes time? And to do that, we take a particular function that we're analyzing. Let's just call this y1. And we assume an optimal solution of y. So this is our optimal curve. We don't yet know what it is, but we're going to compare every other function to it. And so the difference between the optimal solution, y, and the curve that we're analyzing, that distance is simply eta from here. Now notice that eta is 0 at the endpoints. So there's no variation from the real curve and y1 at the endpoints. Okay, we're going to use that fact here during our derivation. So now let's take the derivative of this with respect to epsilon. We know from multivariable calculus that because f is not dependent on epsilon, we can simply pass the differential operator inside the integral. And so we would get partial f over partial x dx over dx, dx over d epsilon, plus partial f over partial y dy over d epsilon, plus partial f over partial y prime dy prime over d epsilon. Okay, so here all I've done is I've differentiated f with respect to each term in f, and then applied the chain rule. Okay, so now here, if I look at what y is, if I differentiate y here with respect to epsilon, all I get is eta. So the derivative of y with respect to epsilon is simply eta. Likewise, if I differentiate y with respect to x, I get y prime is equal to y naught prime plus epsilon eta prime. Then if I differentiate this with respect to epsilon, I simply get eta prime. So this term is simply eta prime. Now, epsilon is not dependent on x. So dx over d epsilon doesn't mean anything. Let's go on. So what I'm going to do is I'm going to rewrite this where just this term is inside the integral. Okay, so we get this. Now, let's actually integrate this. Okay, so I would get this times the derivative of this. I'm sorry, this times the integral of this. Now the integral of eta prime is just eta, minus the integral of eta times the derivative of this. And I've integrated over the bounds. Okay, now when I plug x naught in for eta, I get 0. The variation is 0 at x is equal to x naught. Okay, there's no variation between the actual curve and any other curve at x is equal to 0. So likewise, there's no variation when x is equal to 0. So this term is always 0. So now I have an integral, two integrals, and the bounds are the same. So I'm going to combine these two integrals. So I get okay, now both terms have eta in them, so I'm going to factor out eta. Dx. So eta can be anything. Okay, we don't have any control over what eta is. Eta can be really any number, or excuse me, any function. And so the only way to make sure, the only way to guarantee that this integral is minimized is to make sure that what's inside these brackets is actually equal to 0. Okay, so the only way to guarantee that for all eta that this integral is minimized is if what's inside these brackets is equal to 0. Okay, now this is what we call the Euler-Lagrange equation. Okay. And it's this equation that we apply to every integrand to derive the minimal, the solution that minimizes this integral. Okay. Now, let's just for reference write down our previous equation in our example, where we had time is equal to the integral of the square root of 1 plus y prime squared dx over the square root of 2g times a minus y. Okay, so what's inside here, our integrand, this is actually our f. Okay, so we would differentiate this with respect to y, and that would go here. And then we would also differentiate this with respect to y prime, and that would go in here. And we would then get an equation that it would just be a differential equation. And so by solving that differential equation, we would get the solution to y. That minimizes time of travel. Okay. Now, this is actually fairly complicated to apply to this type of integrand. There's an easier process for this type of integrand that we can use. And to do that, we have to derive the Beltrami identity. So let's go ahead and do that. Okay, so this is our Euler-Lagrange equation. Let's take a look at differentiating f with respect to x. Okay, we know that this has to be equal to the partial derivative of f with respect to x plus the partial derivative of f with respect to y times the derivative of y with respect to x plus the partial derivative of f with respect to y prime times the derivative of y prime with respect to x. Okay, so let's just go ahead and replace this by y prime and this by y double prime. Okay, now let's go ahead and solve for this term here. Okay, so we're going to get partial f over partial y. Now let's just put the y prime out here. So that's this term. And that's going to be equal to df over dx minus partial f over partial x minus partial f over partial y prime, y double prime. Okay, so now if we multiply this by y prime, okay, we see that I can move this to the other side, and then we just get these two terms are equal. Okay, so this is the same as this, and so this has to be equal to this. Okay, so I'm just going to erase this here and write y prime d over dx of partial f over partial y prime. Let's go ahead and set this equal to 0. And so I'm going to move, I have a plus here. And so I'm going to get a minus because I've moved that over. And this is equal to 0. Okay, so now if I take this and I put it out front, so I have a negative out in front of it, I can rewrite this. I can rewrite everything that's left as I'm going to, this is equal to 0. So I can rewrite this in terms of this. Okay, just to make sure that this is correct, I have minus partial f over partial x, which is what we have here. Now I would get d over dx, excuse me, I would get df over dx, which is this term here. And then applying the product rule, I would take y double prime times f of y prime, which gives me y double prime times f of y prime. and it would be a minus. And then I would get minus this, this times the derivative of this. So I would get y prime minus y prime times the derivative of partial f with respect to y prime, which is what I have here. So this is just another form of writing this. Now we see that if f is not explicitly dependent on x, so if f is just a function of y and y prime, then this term is 0. And so I'm left with this. And so by integration, I get this. And this is what's called the Beltrami identity. So if I have an integrand f that is not dependent on x, explicitly dependent on x, okay, then I can simply use this equation to find the extremals. Okay, so f minus y prime, f of y prime, is equal to some constant c. Okay, so let's just write this up here. Okay, so now going back to our original example where we had t is equal to this guy here. Okay, and again, the integrand is f, and it's not explicitly dependent on x. And so I can apply the Beltrami identity. And so I would simply get that the square root of 1 plus y prime squared over the square root of 2g times a minus y, that's f, minus y prime times the derivative of f with respect to y prime. So I would I'd have y, and then I'm differentiating, so I would get this, 2y prime over 2 times the square root of 1 plus y prime squared. So I'm just differentiating this first part here, the part that has a y prime in it. So I would get 1 over 2 square root of the integrand times the derivative of what's inside. So I'd get 2y prime. And then this denominator doesn't have a y prime in it, so it just tags along. Okay, so these 2's cancel out, and I can combine the y primes. So let's just squared, and that's equal to some constant c. Okay, so I would get this. Now let's multiply by the LCD, least common denominator. And so this term here, we can see that the velocity components would cancel out. And so I would have the square root of 1 plus y prime squared times the square root of 1 plus y prime squared. So that's just going to give me, for this term here, 1 plus y prime squared. And then obviously here, the denominator cancels. So I'm just left with a minus y prime squared. And then this is going to be equal to c times this, which is the square root of 1 plus y prime squared times the square root of 2g times a minus y. Let's see here. Looks good to me. And so now what we can do is obviously here these two cancel out, and so I have 1, and I can divide it by c, and then I'm going to square it so that it's equal to 1 plus y prime squared times 2g times a minus y. Okay, so I've just square both sides. So now I can divide by 2g. And distribute or multiply through. Factor this out. So let's rewrite this to where we have a minus y. Okay, so this is going to give me 1 over 2g times 1 over c squared is equal to a minus y plus a y prime squared minus y times y prime squared. Okay, so now let's factor out the y prime squared. So I get equals a minus y plus a minus y times y prime squared. Okay, so now let's solve for y prime squared. So I get 1 over 2g times 1 over c squared minus a plus y divided by a minus y all to the 1/2 is equal to y prime. Okay, so now if I rewrite this as dy over dx, okay, then all I have to do is multiply by dx and divide by this term here, and that would give me a function that's only dependent on y and a function that's only dependent on x, and I can integrate both sides. And then by solving for y, now we get the solution to the curve that minimizes time. That's not necessarily something that I'm going to do. That's more of a differential equations thing, not a calculus of variations. So I'm not going to go through those steps. I just wanted to demonstrate how the calculus of variations can be applied to derive extremals.